Now we're going to introduce something called the dot product. The dot product is the first of two different ways that we have of multiplying two vectors. Now, multiplying two vectors is going to work a lot differently than normal multiplication. And in this case, well, let's see what happens. The dot product of the vectors a and b is the number a dot b. It's written as a little dot b, and it's defined by a dot b is equal to, in two dimensions, a1 times b1 plus a2 times b2. So I multiply the x components together, the y components together, and I add the result. In three dimensions, I just add on the z components. So a1 b1 plus a2 b2 plus a3 b3. Multiply the x components together, the y components together, the z components together, and add them. Note, this is a number or a scalar. It is not a vector. So I'm not multiplying two vectors together and getting a third vector. I'm multiplying the two vectors together under this dot product, and we get a scalar, a number. Let's do some examples of evaluating dot products. So first, let's take 2, 1, dot, negative 3, 2. So I take 2 times negative 3, and I add to that 1 times 2. It's negative 6 plus 2, which is negative 4. How about 3, 2, 4, dot, 2, 1, negative 2? So 3 times 2 plus 2 times 1 plus 4 times negative 2. That simplifies to 6 plus 2 minus 8, which is equal to 0. So here's a weird thing. You can have two non-zero vectors. Those are most certainly non-zero vectors. None of the components are equal to 0, but when you multiply them together, you can end up with the number 0. So that's a little bit weird. C. Let's take I minus 2j dot 2y plus 3k. Let's remember that the coefficient on I is the x component of a vector. The coefficient on j is the the y component of a vector. The coefficient on k is the z component. So over here the coefficient is 1, 2, so 1 times 2 plus coefficient on j is negative 2. There is no j over here, so its coefficient is 0, so negative 2 times 0. There's no k over here. Here it's 3, so 0 and 3, 0 times 3. Multiplying that together, adding up, I get 2. Great. So here are some properties of the dot product, and this first one is pretty straightforward. Maybe you want to sit down and think about why this is true. A dot A is equal to the length of A squared. In fact, why don't we just call that question number 3, which is, why is that true? Figure it out. Okay, it's commutative, that's normal. It's associative, that's normal. Also, it is associative with scalar multiplication. I can multiply a scalar against the vector first and then take the dot, or I can take the dot product and then multiply by the scalar. Finally, and this is something that we would kind of expect, but it's true, the 0 vector dot any other vector is equal to 0. Notice, though, that this is the 0 vector, this is the number 0. This is not a surprise because the components here are all 0, so I'm multiplying zeros against whatever, add them all up, I get 0. But again, vector, number, vector, number. Okay, so here is another fundamental fact about dot products. In fact, sometimes people take this to be the definition of dot product. So A dot B is equal to the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle between A and B if we represent them, for example, as position vectors, both with initial point at the origin. Okay. Fantastic. So this gives us, let's think about what this does for us. On the one hand, certain representations of vectors, we might be given magnitudes and angles. So it's going to be easier for us to evaluate dot products using this fact. Conversely, if we're given vectors in terms of their components, we can easily compute the dot product, we can easily compute their magnitudes, and so we can find the cosine of the angle between them, And from there, you can figure out the angle by taking arc cosine. Anyways, let's do an example of this. Let's take A dot B, where A is this vector starting at the origin, going to 1, just doing two-dimensional vectors here. And B is this vector going from 0 to, this is supposed to be the unit circle, which is suggesting that this also has magnitude 1. Both of these vectors have magnitude 1, and it's making an angle of pi over 4 to the negative x-axis. So what is the angle between A and B here? Here we're going to have theta being equal to pi, which is the angle between A and the negative x-axis, minus pi over 4, so 3 pi over 4. And like I just said, this is the unit circle, so A and B both have magnitude 1. So A dot B is the magnitude of A times the magnitude of B times cosine of 3 pi over 4, which is 1 times, go ahead, compute it out, whatever, cosine of 3 pi over 4 is negative root 2 over 2, which gives us negative root 2 over 2. Your alternative would have been to compute whatever the coordinate of this point is here, and then go from the definition of dot product. Now let's apply this identity backwards. Let's let A be the vector 1, 0, 1, and B be the vector 0, 1, 1. So A is this vector with components 1 and 1 in the xz plane. B is this vector with components 1 and 1 in the yz plane. And if you sort of draw your own picture and think about it, I don't know what angle you think that looks like to you, but I mean, if I were to just guess, frankly, I don't know what I would guess. Take a guess. Think about what it might be. Anyway, so we can find the angle theta between them by using this dot product. So the way we do that is we solve for cosine. We had that A dot B is the magnitude of A times the magnitude of B times cosine of theta. Divide both sides by the magnitude of A times the magnitude of B. And we have that cosine of theta is A dot B divided by the product of their magnitudes. Now we go ahead and we compute the dot product and the magnitudes. A dot B is 1 times 0 plus 0 times 1 plus 1 times 1 is 1. The magnitude of A is the square root of 1 squared plus 0 squared plus 1 squared, so that's the square root of 2. Pretty much the same thing for the magnitude of B. So plugging all this in, we have that the cosine of theta is A dot B, which is 1, times the product of the magnitudes, which is root 2 times root 2, which is 1 over 2. What value of theta has cosine equal to 1/2? That is pi over 3. Is that what I would have guessed? I don't know. I didn't guess anything. So no, I really had no idea. But this shows that it's actually pretty quick and painless to do these sorts of geometric computations using the dot product.